Alright, welcome back everyone. It's time to enter a new chapter in the DB2 course. This is 06 buffering and caching. And this is a topic that is super relevant when it comes to the runtime performance of query and update evaluation in relational database systems. No acceptable performance of these systems without any form of buffering and caching. And we will see that buffering and caching are two sides of the same coin, two words that discuss concepts that are really close to each other. So let's see where the discussion leads us. This is all motivated by a fact that we've already looked at, but I want to recall it here. It's the size and the latencies of the memory subsystem that we face in modern computers. And there's a conundrum here. There's a dilemma here that we are facing, and it's about memory size and memory speed. So what you'll typically find in your systems is that you got parts of very fast memory in your systems, but unfortunately these really fast portions of memory are tiny. There is much larger capacities of memories or parts of the memory architecture in your systems, but unfortunately these tend to be slow. All right, so that's a real dilemma, and we have to deal with that, and have to build database systems that can deal with this crucial, sad, true fact of computer architecture today. All right. So the real core of the problem are the enormous latency gaps that we see when we address different parts of our memory architecture. There is, in the best case, accesses to the caches next to the CPU, next to the processor in your systems. So if we hit the L2 cache in your system, then you can expect latencies, that is waiting times until the memory reference can actually be resolved and the bits of memory are really available to the CPU. Such latencies can be around 2 to 3 nanoseconds. All right. And because nobody out there can really appreciate and grasp what the nanosecond means, we have, if you recall, translated these latencies into timescales that a human can really understand. So back then we translated these 2.8 nanoseconds in something about around 7 seconds. So that would be a unit of time that's relevant now to us. All right. Unfortunately, the CPU L2 cache, with its really acceptable, very fast latency of less than 3 nanoseconds, is really small. So what you will typically find in your systems is something of a few megabytes of memory that can fit into the CPU L2 cache. Okay, that's not much. That's something, and we can work that, but it will probably never hold an entire database. When we cannot find the necessary bits that we need to access in the cache, then we might find them in RAM, so in the primary memory of your system. But that may yield latencies, so wait times that are about a factor of 50 longer, so 100 nanoseconds we are looking at here. That's considerably longer. So in a human timescale, that might be something of some minutes, not seconds, but minutes already. But RAM is larger, so larger portions of the database would fit into RAM. So several gigabytes, for example. So the system I'm currently working with has 16 gigabytes of RAM. Maybe your cool PCs at home or systems at home had even larger RAM sizes, but typically you will find something around these gigabyte ranges today. Okay, so some databases may fit in this in such RAM sizes, and it's actually one of the claims of MonadDB that it performs best when the really relevant part of your database fits into RAM. So in a main memory database system, operates under the assumption that most of the relevant, of the significant, of the interesting parts of your database really do fit inside this memory size. But larger databases and all the persistent parts of the database, so probably the far the largest part of your database, will need to fit on some secondary memory. So in any of these two below here. These can deliver much larger sizes, so we will probably start to measure in the range of terabytes here. All right. But the access latencies really make a big jump. So we are going from the 100 nanosecond scale into the about 100 microsecond scale. So the waiting times increase by a factor of 1000 from row to row. So waiting for bits that have to be delivered from SSD will make us wait 1000 times longer than finding the same bits in RAM. So this is a real performance hit, and it makes access to SSD a real pain for the system, and a good system should better try to avoid too many SSD accesses. It's better to find the relevant stuff in RAM or even in the L2 cache. So on the human scale, we are now entering waiting times that are beyond acceptable, like in the range of days. And it's even worse, of course, if we have to wait for the rotating hard disk drives, the classical hard disk drive, secondary memory drives that were prominent and widespread just even a few years ago. The latencies would be in the range of milliseconds now. So going from nano to microseconds is a factor of 1000. This would be another factor of 1000. Maybe looking at these numbers, it's in fact a factor of 100 that we have to wait longer, but multiplying all of these waiting times, comparing HDD to CPU L2 cache, we have a waiting time increase of factor of like 500,000 here. This is really super relevant and really makes all the difference. Of course, we would be able to store lots of stuff there. So HDDs would make good storage alternatives for really large databases. What becomes clear now is that we will probably not be able to build a database system that entirely lives with its data in the L2 cache or even in RAM. It's just not feasible. It's just not possible, and probably way too expensive to build CPU caches or even RAM that is capacity-wise comparable to these secondary memory alternatives. We will have to live with all of these components. We will not be able to build a cache-only database, but SSDs and HDDs will remain a significant part of the architecture of your systems and of database systems. The lion's share even of data will live in slow memory, and only selected data fragments will probably fit into really fast memory. And the question is, which fragments of the database shall we choose to live in RAM or even in the cache? It will only be a tiny fraction of the database probably. And there are two observations here that come to help us. And they are both about a notion of locality. Spatial locality discussed on this slide, and temporal locality discussed on the next slide. Okay, so spatial locality refers to an observation that the accesses to memory that the database system typically performs are not completely random, but they observe a notion of spatial locality. If we access memory at some address M at a particular point, then it's very probable, it's not a given, but it's very probable that the next RAM accesses will be in the vicinity of M, like M plus or minus delta M, where delta M is typically very small. Maybe delta M is only a machine word size away. And that might happen when we, for example, scan an array. An array located at address M, or some of the elements one of the elements are located at address M. The adjacent elements will be in the vicinity of M, spatially local around M, and a forward or backward scan through the array will hit memory references in vicinity of M. And this is an observation that is crucial because it gives the system a hint about the value of keeping memory bits around address M in faster memory. If we have just accessed memory at address M, it might be valuable, it might be very clever to also hold the addresses around in the vicinity of M also in faster memory. They will be processed and accessed in due course, and that's very probable. All right. So iteration over an array would be one of these very typical iterations. The scans that we've already discussed when we were looking at the internals of MonadDB, of the projection operator, for example, they behave like this, and they lead to memory accesses that exhibit spatial locality. There's also a very nice thing to observe about the block I/O that we are performing when we are talking to secondary memory devices. As you recall, we are not accessing particular individual memory addresses, but we are always moving blocks from secondary memory into primary memory. And regarding spatial locality, this is a good thing to do, because bringing in a block containing a particular memory address M from secondary memory into primary memory, from SSD to RAM, for example, will also bring all the addresses around M, or maybe after M, into RAM. And that's a good thing. Accessing these addresses in the vicinity of M will not lead to new block accesses, because we've already performed the necessary I/O block memory movement. So the number of block accesses that we will see in such a system are probably much lower than the number of memory accesses that our system will perform. And that's a good thing, because these are so damn expensive. Okay, so spatial locality will help us to save on the number of block accesses when we do block I/O. The other notion of locality that we are observing and that we can benefit from is temporal locality. So if your system accesses memory at some address M, then it's very probable that the next accesses to the same address will be close in time, in the near future. So if the last access to M happened at T, the next access might happen at T plus delta T, where delta T again is some very small time range. All right. So if M is valuable and in focus by the system now, it's very probable that the further access to M will happen very soon. So temporally local. As long as the longer the time frame goes and the longer the access to address M lies in the past, the less probable it becomes that M is relevant again. All right. All of this is a general observation that might, of course, be not true for one particular access pattern or for a particular operation that the system performs, but it's a general observation that generally holds. All right. Because of this, the CPU itself, but also the DBMS, tries to track the frequency and the recency. So how long ago have been these accesses to address at address M, and how often do they occur? All of this is being recorded by the system as input to algorithms that decide whether it's valuable to keep the addresses at M in the faster levels of memory. So, for example, RAM or even the CPU cache. Okay, we will only fit very small bits of memory in these faster levels. So we better have clever and reasonable algorithms that decide, given on spatial and temporal locality, that that a particular address is not valuable or will be valuable again in the near future. All right. And such decisions, which stuff to keep in the faster levels of memory, is something that concerns multiple levels of our system. If you flip back to the slide before, or if you look at this table below, then you will see that keeping stuff in RAM is probably favorable about keeping stuff in this slow secondary memory, but RAM will only hold a fraction of the actually bits. So for this particular machine I'm running on and currently recording this video on, RAM is by a factor of 64 smaller than SSD or HDD. So only a small fraction of the contents of SSD or HDD will actually fit into RAM. Which particular bits of the SSD will be mirrored into RAM is a crucial question, and we need some clever algorithm, some clever decision procedure to decide on the actual portion of SSD or HDD that is mirrored into RAM. And it's the same on the level above that. So the cache, the CPU L2 cache, close to the CPU already, is unfortunately very much smaller, significantly smaller than RAM. So on this particular machine, it's by a factor of over 65,000 that cache is smaller than RAM. So really deciding on the parts of the very tiny parts of RAM that we can hold in the deep CPU cache really will make a difference here. We can even move closer to the CPU from L2 to L1 cache, and L1 cache will deliver, even the L1 data cache will even deliver better performance than the L2 cache. But again, we are facing severe size restrictions here by a factor of 1/8 of if we are basing the numbers on this particular MacBook Pro here. Okay, so we will need algorithms on multiple levels, so that decide the SSD contents that is mirrored into RAM, the RAM contents that is mirrored into cache. All of this are relevant questions that will bother us repeatedly in constructing an efficient database system. Okay, to investigate this and to stay true to the core idea of this particular lecture, that we will be using queries to investigate the internal behavior of PostgreSQL and MongoDB, we will do something different now, but now define a set of queries that are performed sequentially, one after the other on the database system, and name that set of query our query probe Q5 now. Okay, such a set of queries would normally be referred to as the query workload faced by a database system. So the query workload is just a fancy name for the set of typical queries, the typical sequence of queries that your database system will face when you operate it on a day-to-day or a daily fashion. All right, so we will have a Q5 query probe workload that looks like this. So we will have a sequence of queries performed one after the other, and you will see that it's constructed like the following. So we will hit the ternary table in both of these queries, and maybe even the other queries that follow here in the workload, and you will see that we will perform these sequences of queries close in time. So temporal locality may come into play here. The system will observe that the same table is valuable, or the bits of the same table are valuable close in time. All right, so that's a notion of temporal locality. And if you look at the projection that we are doing here, the projection of attributes that we are doing here, the columns that we project on, then you will see that there is also some overlap. So both of these queries refer to the column A. All right, there are some unique references to column B and C here, but there's overlap in column A. So some spatial locality is probably also being observed, that addressing or accessing pages of memory or locations of SSD that hold the A column may be valuable for more than one query. So that's a notion of spatial locality that we probably be observing. All right, and if the systems do anything right, PostgreSQL and MongoDB, we hope that we can save some I/O effort in producing such a workload, such a sequence of probe queries, and that the effort invested in evaluating this very first query is not completely wasted when it comes to the evaluation of the second query, which is similar, and maybe the third query in the workload that is similar again, and so on. All right, so the upcoming videos will investigate how PostgreSQL and MongoDB deal with this particular situation, and this will lead us to an in-depth discussion of buffering and caching. Looking forward to work with you through this chapter, and take care and see you around.